Hello and welcome back to another Calculus 3 multivariable calculus video. Today we'll be going over maximum and minimum. Well, first of all, what is maximum and minimum? Maximum and minimum is, well, it's kind of in the name. It's the maximum of a given function in 3 dimensions, and we dealt with this in Calculus 1 and 2, sure, but in Calculus 3, it's a completely different photo. It's a whole different beast, if you will. It deals with more than one variable, with a more complex function. So yeah, that's what's different. What is its maximum minimum? Well, it's essentially optimization. Think about this in like thermodynamics or finance, or so. I guess for these two examples, with maximum minimums, well, thermodynamics wise, we can find the hottest point on a surface now that we have a 3 dimensional ability to graph, so to speak, I guess. We could find the hottest point and the coldest point of a surface, maximum and minimum of temperature. And financially, well, what if we had a company when we were trying to minimize the cost of making a box? Well, this is when calculus 3 may come in. So the why we're doing this, well, it's pretty much in the name. It's to find maximum minimums, and it's in the what as well. It's to optimize. I'm not going to get really into too much in the why because it's kind of, once again, in the name, it's kind of intuitive why we might want to maximize and minimize some certain functions and find what the maximum and minimums are, and overall, why we might want to optimize. So the biggest question within this is how. The other two are kind of intuitive, but this one maybe not so much. Well, first of all, we're kind of going to want to take the calculus 1 and 2 route. What we're going to do is we're going to identify critical points. We're going to classify those critical points, and we're going to conclude whether or not it's a maximum or a minimum. We did this in calculus 1 for sure. Calculus 2, not so much, but in Calc 1, we definitely did these, and although the process is different, it's the same concept. You'll find that I'm a very big fan of 3-step processes. So, identifying critical points is when the partials are equal to 0, meaning we take the partial of the function with respect to x and the partial of the function with respect to y, set them both equal to 0, and assuming it gives us 1 point, that's going to be our critical point. Or if it gives us multiple, we're going to have multiple critical points in which we're going to have to test. Classify critical points. We're going to be using the second derivative test. Once again, something that we are familiar with because of Calc 1, but it's going to look a little bit different because, once again, we are in 3 dimensions, right? So we are going to have our partials, right? We're going to have partials within our second derivative test. We're going to take second partials. I will be getting more into that right now. And then finally, we're going to conclude maximum and minimums based off of everything that we're given, based off of our critical points, based off of the values that those critical points give us within the function. That's essentially going to conclude whether or not we have a maximum or minimum, or in some cases, it may be unclear, it may be inconclusive, or it may even be something that we like to call a saddle point. So I guess we're getting into the meat and potatoes over here, so to speak, is the theorem is essentially f of xy has a critical point when the partial derivative of x is equal to 0 is equal to the partial derivative of y. This does not guarantee extrema. This only guarantees that it's a critical point, essentially. I mean, it's not going to guarantee that it's a local maximum, or it's not going to guarantee that it's a local minimum. Just because we have one critical point doesn't mean that it has to be either of those things. So it does not guarantee extrema. And if this isn't extremely digestible to you, basically what this is saying is that there's critical points when both partials are equal to 0. So let's go ahead and get to the second derivative test, which is the second part of my 3-step process. Second derivative test, well, let's let d of xy equal the double partial of x times the double partial of y minus the partial of xy squared. What this is called the discriminant. This is essentially just the second derivative test. Commonly, it won't usually typically give you a function. unless we have a pretty high power, high order x and y, it typically won't give us a function. But in the times that it does, I guess we'll cross that line if we get there, right? Cases. This is something I want to talk about here because we can have all this information, but if we don't know how to interpret it, then it's essentially useless, right? So if the discriminant is greater than 0, this is what we want here, right? Well, if the discriminant at a critical point is greater than 0, then what? Well, we have to test then our second partials. We can either do our second partial of x, or we can do our second partial on y. Just for convention, I'm doing second partial on x. If second partial in x is less than 0, then it's a local maximum, and we can kind of intuitively understand why that is when we look at the calculus 3 or the calculus 1 picture. Whenever we have a polynomial that's negative, well, it's facing downward, meaning what? Meaning that's essentially it's going to be concave down, right? Meaning what? It's a maximum. And conversely, it's the same concept. If our second partial in x is greater than 0, then it's a local minimum, meaning what? Well, it's concave up, meaning what? Like we established in calculus 1 intuitively, we kind of understand now that that's going to be a local minimum. If our discriminant is less than 0, then we have a saddle point. Not really much testing that we have to do there, meaning it has mixed concavity. We do not know whether it is a maximum or a minimum. We know that it is mixed concavity, and therefore we know it is a saddle point. And if our discriminant is equal to 0, then our test is inconclusive. Obviously, some of these tests aren't always conclusive, in an ideal world for sure. But in calculus 2, for sure, we know that there are a lot of tests within mathematics that make it just inconclusive. So that's essentially what the discriminant is, and that's what the cases are. Pretty big giveaway is if essentially what our discriminant is. The sign of the discriminant is really going to tell us everything that we are going to need to know in most cases. Obviously, we're going to have to check our second partials, but that won't be too big of a problem here. Also, if any of my fellow engineers here recognize this Python that I've got going on here, obviously it's not exactly, but I got if, else if statements. Maybe I a little bit nerded out on that one. All right, whatever. Let's get into an example here. Let me take a sip before we start doing some numbers here. Find and classify local extrema of f of xy is equal to x squared plus 2y squared minus 4x plus 4y plus 3. Well, how are we going to do that? Well, we're going to go ahead and just copy down our 3-step process up here. Why not? Let's do it. Copy right here. Well, step 1, we're going to find our critical points when the partials are equal to 0. So what are we going to do? Well, step 1, we're going to find our partial of x and our partial of y. We're going to set these both equal to 0. So partial of x is going to be what? 2x minus 4. Yeah, 2x minus 4. Partial in y is going to be 4y minus 4 plus 4. Yeah, 4y plus 4. Set these both equal to 0. 2x minus 4. 0 is equal to 4y plus 4. So we have 2x equal to 4 divided by 2x equal to 2. And then we have 4y is equal to negative 4 divided by 4. Y is equal to negative 1. Well, this is pretty nice. We only have one critical point here at the point 2, negative 1. Well, that's nice. Oh, sorry, wait. Did I mess up here? It's 4y plus 4. Yeah, we're good. All right, 2, negative 1. This is our critical point that we got going on here. Let's just go ahead and get into it. That's step 1. We have our critical point. This is essentially what we're going to be testing at. 2, negative 1. Well, let's go to step number 2. What is that? That's going to be our second derivative test, classifying the critical points. Well, let's do our second derivative test really fast. Our discriminant is going to equal our double x double y minus our fxy squared. Well, what is our double partial in x? Our double partial is just going to be, well, we just take the partial again. Well, that's just going to be 2 times our double partial in y. It's going to take the partial of our partial. We have going to have 4. We're going to subtract that by f sub xy. No matter how you do it, this is going to be 0. If we take the partial of our partial in with respect to y of our partial of x, sorry if that's a little bit of word soup there, this is going to be 0. I mean, same concept with f sub y, so this is going to be minus 0. This is going to be 8. So our discriminant is equal to 8. 8 is just going to be what? That's going to be greater than 0, meaning we're talking about local maximums and minimums here, right? Well, let's go ahead. Let's do our other test that we have to do. Well, what's our second partial of x? Well, that's going to be greater than 0. That is 2, meaning what? Well, we're going to go ahead and go up to our little chart here. That's greater than 0. We're going to have a local minimum here at 2, negative 1. We could definitely, just pretty intuitive perhaps, why that is, like I stated prior. So, yeah, that's a pretty simple problem. So, therefore, we can essentially conclude that we have a local min at our point 2, negative 1. That is briefly maximum minimums. I will be getting into much deeper depth in the following video about Lagrange multipliers. Get ready for that one. That's going to be a doozy. Yeah, thank you very much.